That's not us. Not at all. So this diagram shows, or depicts anyway, a salt molecule, a salt crystal, made up of lots of these ionic molecules all stuck together, being basically ripped apart by water molecules. So remember yesterday we reviewed anyway, the polar nature of water molecules and how they have a partial positive side and a partial negative side. That allows water to be a very good solvent. A solvent is a material, generally a liquid. Sometimes we can have gases that are solvents, but generally we're talking about liquids. But it's a material that can dissolve other materials. And because of its small size, its polar nature, water is one of the best solvents that we know of. So when you put the salt in and it dissolves, what happens is the water molecules take the ions apart, separate the ions, and surround them. And we can see in a chlorine ion right here, the water molecules are all oriented so the positive hydrogen atoms are pointed towards the negative chlorine atoms, so they kind of surround it like that. With the sodium ion, Riley, with the sodium ion, all of the oxygen atoms are pointed towards it because they have the partial negative charge. So we basically surround them. This is what we call solvation. Okay. Now what we're showing here is a specific type of solvation called dissociation. And it's called dissociation because it actually pulls the ions apart. The ionic compound, the ions that make up the compound actually get separated in dissociation. Sugar can dissolve into a liquid, into water, but it doesn't get pulled apart because it's not an ionic solvent. So sugar would go through solvation to become a solution, but it's not going to go through dissociation. So dissociation is a specific type of solvation where the ions actually separate. So, water in this case is acting as the solvent, and so salt would be the solute. Solute is the thing being dissolved. Now, 9 times out of 10, when we're talking about a solute and a solvent, we're talking about a liquid solvent like water and a solid solute like the salt. But you definitely can have liquid solutes as well. For example, ethanol, alcohol, dissolves into water very easily, which is why we can have wine and beer and all that kind of stuff. Now, what you call the solute and the solvent is going to depend on the volumes. So a 50-50 mixture would be kind of hard to say, but if you had 80% alcohol and 20% water, then you would call the alcohol the solvent, the water the solvent. Everclear is just a mixture of water and alcohol. Oh, that's what you would call it. I see. I see what you did there. Okay? But for there to be solvation, obviously the thing has to dissolve. We talked about our solvation rules, or the word that can't come to my head right now. Solubility rules. Solubility. I understand. You get old, it happens. So the solubility rules, that shows us the things that will dissolve easily and the things that don't and stay as a solid. Okay? Now, the cool thing about ionic compounds, also called salts, when a salt dissolves in a fluid, it can form an electrolyte. Okay. Now, what we call salt is just a specific type of salt made of sodium and chlorine. Basically, any ionic compound is technically a salt. Magnesium chloride is a salt. Calcium phosphate would be a salt. Anything that is made up of ions is that can be separated is going to be technically a salt. We talk about it in chemistry terms. So here again, we're going to stick with table salt, the sodium chloride. That sodium ion that is surrounded by those water molecules is able to move. And if we set up an electric field where there's a positive charge over here and a negative charge over here, because the sodium atom is positive, it's going to be repelled by the positive charge, it's going to be attracted to the negative charge, and so it's going to move. It's going to move across towards that negative charge. And if we have a moving electrical charge, that's electricity. Now, in solid wires, electricity is actual electrons moving between metal atoms. Okay, so that's a little bit different situation, but you can definitely have electrical flow with moving ions. That's why salt water conducts electricity so easily. Because the ions are able to move in the water and be attracted towards the negative end, repelled by the positive end.
If lightning strikes, salt in motion. Get shot.
Absolutely. Even in what we would consider fresh water, because that's not pure water. There's all sorts of dissolved ions.
But it's faster than salt water.
That's true. Yeah, the salt water would probably conduct it faster. But that's why one of the reasons why it's lightning out on water, you're supposed to get out of the water. The other reason is you're the tallest thing out
there. Yeah, you probably shouldn't go golfing in the middle of the ocean.
That's yes.
In the middle of a lightning storm.
Words of wisdom right there. Don't go golfing in the middle of the ocean.
During a lightning storm.
So if the lightning's in England, you're sitting on the beach in New York.
The electricity would be...
No, because it spreads out and it dissipates. Yeah, no.
Oh my God, who ripped ass?
I hope that shows up on the video. So...
Where are you recording?
I said I'm going to try to get into the habit of recording all of them, so if there's something you want to go back to the video.
Oh, I thought it was chemistry. I really don't care now.
Anyway, you hear about like Gatorade and Powerade, they say that they have electrolytes to put back into your body, and that's actually important. When you sweat, you lose salt, and that salt is important for conducting electrical signals through your muscles. In anatomy, those of you in anatomy will learn about how signals are conducted through muscle pathways and through neurons, and it's all about moving ions. And so if you don't have those ions that are dissolved that are able to move, you can't conduct those electrical signals.
So then would Gatorade conduct electricity?
Sure.
Really? Should I use that?
Well, I mean, now how well it conducts, I don't know what the concentration is in there.
Gatorade would...
That would be something that, an easy experiment that you could try.
Gatorade would conduct better than Powerade. There's more salt in it.
Okay, that could be. But, I mean, the thing is, when they talk about, Gatorade being so good for you and everything, it's really not. You're better off to...
Drink some salt water.
I would not drink salt water.
Lightly salted water.
What I was going to say, you'd be better off to drink the same amount of regular water and eat some crackers or something with a little salt. Okay, let's see. So we talked about that.
H2O. H2O.
Okay, I skipped over the picture of the battery and the water. I mean, we did that experiment in class before. Strong electrolytes are things that are going to be able to dissolve and disassociate completely. I don't know if we'll actually get to talking about acids and bases in here. We are 3 weeks behind where we normally would be. But strong electrolytes, like strong acids and strong bases, all of the molecules get pulled apart by the water or the other solvent. And salts, for the most part, pretty much, if they are soluble, a salt is going to completely dissociate. So those things are strong electrolytes. Weak electrolytes that don't conduct very well are things that don't disassociate completely. So weak acids and weak bases. When we start talking about acids and bases, if we get there, you'll see that some of them are going to not completely separate into ionic form. They'll stay together in a kind of a dynamic equilibrium. Some of them are going back together, some of them are getting pulled apart. And so weak acids and weak bases are not going to be as good conductors because they are not completely separated. And if they're not separated, then the ions are not going to be attracted because they don't have the charges. So these things, these types of things like, say, a good example of a weak base would be hydrofluoric acid. Thanks. So hydrofluoric acid is made up of a hydrogen ion and a fluorine ion. But when you put this into water, the water can't separate all of them. Okay, we'll learn to calculate if we get there how many of them actually get separated by what's called a dissociation constant. But some of these are going to get stuck together. Some of them will get separated into H plus and F minus. Okay? Just as I want to say, based on the dissociation constant, we could say, as a rough approximation, 80% would not get dissociated. The other 20% would be. So these molecules here can't be electrolytes. There's nothing that can happen as far as the electrical charge goes because they have no charges on them, and they're not able to move towards those positive and negative ends. But the ions that do not dissociate and separate, those can. So that's why this would be a weak electrolyte. Something like, say, H2SO4. Basically, every single one of these molecules is going to completely separate, and that's why it would be a strong acid and a strong electrolyte. Okay, any questions there? All right. We'll move on and talk about hydrates. So the stuff in this chapter is just kind of a mishmash of certain things that it's good to know, not necessarily connected to each other. Okay, a hydrate is a compound that incorporates water into its solid form. Probably. It's not a made-up word. It's just grossly misspelled. So, what does it mean to incorporate it into its solid form? Well, a good example would be magnesium sulfate. I should really have you guys write these formulas for practice. But magnesium sulfate, if you create that by a chemical reaction, you could set up some type of chemical reaction, a double displacement where you would make magnesium sulfate. When it forms a solid, it actually is going to use water molecules to help build the crystal of that solid. And so it isn't just magnesium sulfate that forms. It's magnesium sulfate, and each sulfate atom, or magnesium sulfate molecule is going to have 7 water molecules that are associated inside the crystal. So if you look at a crystal of magnesium sulfate, every molecule of MgSO4, there's going to be 7 water molecules that are kind of helping build that crystalline structure. And the way we write it is we put a dot after, and then we write 7 H2Os. This shows that this isn't really part of the chemical formula, but it is associated with it in the solid. That's just how the water molecules, with their polar nature, surround the magnesium sulfate in the crystal. And as far as
It's always going to be 7.
for this, yes. A different compound that could be 3 or 5. How?
Good question.
Well, okay. You're asking how do you know how many are going to form with it?
Right.
That's gonna, that takes a close study of molecular structure.
Okay, so we're not going to have it.
No, but what you need to know is how to notice that this is a hydrate, with the dot and everything, and how to name it. Okay.
Magnesium sulfate, heptahydrate, isn't it?
Yes, that's how you name it. You use the prefixes that we learned for the molecular compounds, and we just put hydrate behind it. Yes.
So is this one pretty much the same as the one on the sheet? There's no 7 on either sheet, right? If you tell that, okay. But there's no 7.
Okay, so that's a different form of the crystal. It's going to only have 1 water molecule associated with it. Okay? So, like I said, the main things that I want you to know is to recognize this as a hydrate. If we went back on the shelves, you would see there are some compounds back there that have the dot and a certain number of water molecules after it. And again, we should be able to name these. So, as Isaac kind of already pointed out, we would call this magnesium sulfate heptahydrate. So, it would be good to run through our prefixes as review. What's the prefix for 1? What about 2? 3? 4?
Tetra.
Tetra. A lot of people got that wrong on the test. Tetra is 4. 5?
Penta.
6?
Hexa.
7?
Hepta.
8?
Octa.
9? And 10?
Deca.
What do people think Tetra was?
3. I had a lot of 3s. Okay, so just as a quick practice, name this compound. Let's see. Let's do. Copper phosphate.
Copper 3 phosphate. Pentahydrate.
Very good, Isaac. Copper, because copper is a transition element, we have to add the charge with the Roman numerals. Since phosphate is a minus 3, the copper has to be a plus 3, so it's copper 3 phosphate. That's review. Then penta
when you read it out, do you have to put the dot on there?
In the formula, yes.
They didn't put it on.
No, there isn't a dotted name.
Yeah, that's what I meant, like when you write out the name.
Oh, no, sorry, that was not a dot.
That was just kind of.
That was just accident. No, in the formula, you have to have the dot in the name even. Okay, so on a test for the naming ones, I would probably have 1 point for doing this, that's the review part, and then another point for doing this, so 2 points for each one. So, that's hydrates. And then the other thing we're going to talk about today is solubility. Okay, we've already discussed solubility in context to whether or not things will actually be able to dissolve or not. But we can also look at solubility as far as the amount that the actual solvent can hold. Okay? And the solubility is going to have to be based on the volume of the solvent. If you take a glass of water and you start mixing sugar into it, and you keep pouring sugar in and you keep pouring sugar in, and even if you stir it, eventually you're going to get to a point where the water just can't hold any more sugar. Basically, every sugar molecule is surrounded by the least number of water molecules that can hold it in solution. And so none of the other sugar molecules can get dissolved, and it'll just fall down to the bottom when you put it in. So you reach the solubility level of that liquid. And all liquids, depending on the solute, are going to have that kind of cutoff point where no more can go in. It is unfortunate.
So, what if you boil it?
If you boil it, what do you mean? If you boil it, you're going to actually remove more liquid, so it'll be able to hold less. Now, up to that point, you'll be able to put more in because the solubility does increase with temperature.
Right. And doesn't like sugar melt or
You have to get sugar pretty high to melt, pretty hot, way past the boiling point of water. So all the water would boil off, and then if you kept heating it,
caramelize.
yes, it can.
It'll mix food size and chemistry.
Food size is pretty much chemistry.
Yeah, it is.
We try to apply tools that don't apply.
Well, no, that's absolutely true. But you'd have to boil a lot of the water off to be able to get enough heat to melt the stuff, because the temperature will stay the same for the water's not. Okay, so the solubility is going to depend on the type of liquid, or sorry, I should say the type of solvent. It's not always a liquid, but also the temperature. Higher temp, you can hold more. Right. But if you have two samples of water and you have one close to the boiling point and one close to the freezing point, you will notice that the one that's close to the boiling point is able to hold a lot more solvent. It's able to dissolve it a lot more because the molecules are basically moving around fast enough. They're able to kind of go in between different molecules and help hold them in solution with easier. Okay. Now, because of this, though, it is possible to make what's called a supersaturated solution. So, if we take something and we dissolve as much solvent in it as we can, we would say that it is saturated, it can't hold anymore. What's cool is if you take a solvent and you heat it up, and you get it saturated so that it can't hold anymore, and then you slowly cool it down, it will actually be able to hold more of the solvent than if you just took the liquid or the solvent at that temperature and tried to mix it. And it's because to come out of solution, basically the solvent or the solute has to have something to kind of start forming crystals. So by taking a liquid or a solvent, getting it to a high temperature, mixing it as much as you can, and then cooling it down, you can have it kind of right at the point where it's just ready to come out of solution, but it's kind of still being able to be held there. That's called supersaturated solution. And if you throw a little something in there, or if you kind of give it a shock so the crystal is able to form, you'll see a whole bunch of it come out of solution very quickly.
So kind of
Do
like
you have a video of it?
I do have a video of it.
Water school.
pushing borderline freezing temperature, and you get like a little bit of shock. We
Yeah.
did that. That was
That's
awesome.
so that's a super cooled. It's basically the same idea.
Yeah, we
It
had
was
a,
awesome.
we had a Powerade sitting out outside the ice or fish house, and we grabbed it and it was liquid, and I opened up the crack or I cracked the cap valves, and
Yeah.
it's cool to watch. It's cool to watch.
My name is John.
My name is John G.
So no, his name was John.
We've got 3 tracks.
Hey, you got a remote.
Zoom in, Rena. Like, I don't know. Go closer. Come on. You can't even see it. Okay, go.
So here he's got a pause this a minute. He's got a supersaturated solution of sodium acetate. He's got it up to a high temperature. He's dissolved as much as he could in there, and then he's let it slowly cool down. Now, because it's a pure solution, basically all those sodium acetates that shouldn't be able to be held by the water are kind of just ready to come out of solution. He's going to throw in a seed crystal, so basically a little chunk of sodium acetate, and that's going to give a place for any other molecules of sodium acetate to kind of form onto and start crystallizing and drop out of solution.
Make the crystallizer. It's not gonna crystallize on your phone.
So realize this has been sitting there all year long like this.
What is it? What is it?
Change it. Well, it's water that has a huge amount of these crystals dissolved in it. It has so much of it that is called supersaturated. It actually is holding more salt than water actually can. It's like oil.
You dropped it in there? Oh! Oh snap! Oh my gosh!
Oh,
That's so
snap.
cool!
Who in the hell used the word
It's
or
like
phrase,
a-
oh
it's
snap?
like a
It is
puffball.
21st century, not fucking that.
Okay, Riley, thank you.
What happened to
This
the
is
bug?
from
What happens if it's still over
probably
there?
10 years ago.
That was just one drop.
Crystals.
Look at it extended from the bottom. Oh, that one's racing. It's racing. Look, that one's jerking. You got it.
Yeah, I get that part.
Want to see my nail? I want my nail to be in the picture. Oh my gosh. Like, this is cute.
My nails are big.
It does look kind of weird. It's so cool. Is this real? They look like feathers. Can we touch it? Are we gonna move it?
Wait till it's all crystal.
You can touch it either way. I touch radioactive things.
So is it hard now or what?
Oh my gosh.
There's still water in
We
there,
can
but
look at it.
the solid in there is kind of overtaking it.
Are you gonna break it off?
Just
It would be kind of, well, if you were to feel it, it'd be kind of like slimy jelly.
Is it cold?
I should have had
so
sides of it.
so there's so much salt in it that 1 more gram turned it all into a salt.
Not cold.
Well,
Yeah.
the salt that should be out of solution, right? It needed a place to start forming the solid. So that's what that first little piece was. He could have threw a first piece of dirt or something in there and just would have made it
With our hand in it?
nastier over time. So it's easier just to throw that seed crystal. Okay.
Why are you listening
Now,
to me?
all he's got to do to reset it is heat it back up so that he raises the solubility level so that more of that salt can fit in there. So it will dissolve, and then let it cool back down to form that super saturated solution.
I was very upset by that.
By what?
Oh, snap.
Do you care what somebody you'll never meet says on a video that you'll never watch again?
Just naturally.
That explains a lot of your problems, Riley.
Who in the hell says, oh, snap?
You could just forget about it.
Okay. The other thing we can talk about is the rate of saturation. It's basically how quickly does the solvent go into solution. If you've ever made Kool-Aid or something like that, you know, if you just dump all the stuff in there right away, it doesn't all just dissolve. It takes time. If you take your Kool-Aid and you let it sit there long enough, eventually all of the molecules would go into solution. But what do we normally do to speed it up? Yeah, we stir it. Agitation.
This is what's wrong with me.
Oh, snap. So, agitation is going to speed up the rate of saturation. It's going to get things into a solution more quickly. And whether you're in food science or you're in chemistry, everybody stirs stuff because we don't want to wait around for it to go into solution all by itself. So, in chemistry, we tend to use magnetic stirrers and magnetic stir bars. So it's a little plate that you set it on that has a magnet in it that spins around. You take this little plastic thing that has a magnet in it and you drop it in your solution and it spins and swirls the stuff up. But that's just a form of agitation. You can do it by hand. I can do that, I guess. I will show you.
Sodium is water.
Okay. Another thing that will change the rate of saturation, of course, is temperature. The higher the temperature, the faster the stuff's going to go into solution. Okay, but also surface area. So we're talking about particle size. Okay, if you take a cube of sugar and you take a packet of sugar grains that have the same mass and you pour them into a liquid, the one that has all the sugar grains is going to dissolve much more quickly because the water molecules are able to get to more of the sugar molecules at any point in time. If you think about the cube of sugar, it has to eat away the outside to be able to get to the inside, so it's going to be much slower to dissolve. So the smaller the particle size, the faster you're going to get saturation.
Mr. Roark,
But
I saw this video where a guy stuck his hand in the sodium acetate and he got a second-degree burn.
yeah, chemical burns are not fun.
Can we watch it?
No.
Can I watch it? Just watch the video on a guy stuffing freaking spring make come out of his tear ducts.
Great.
The hell is wrong?
He's from California.
Probably get cancer.
Okay, then the last thing we need to talk about today.
Tori just like to be like upset.
when one liquid dissolves into another or mixes into another, what you can see is that volume is not considered. So if you take, say, 50 milliliters of alcohol and 50 milliliters of water, and you mix them together, you'll actually find that the total volume of the mixture is like 98 milliliters. Because when you mix them and the alcohol dissolves into the water, or vice versa, I mean, at 50-50, it's hard to say which one's the solid, which one's the solid. But as they mix together, they're actually going to be able to fit in smaller spaces because of how the molecules surround each other. You get a slightly lower volume. So volume is not always considered when you're mixing things together.
But the amount is the same.
The mass would be the same. Yeah, the mass would not change, but the volume would. So you're actually changing the density when you make a mixture. Okay? And we can also have gases that are dissolved in liquids. Gases didn't dissolve in liquids, then fish wouldn't be able to breathe. Fish extract oxygen that is dissolved in the water out through their gills. Fish have to breathe too, they just get it from the water instead of from the atmosphere.
It's like a secondary breathing apparatus.
But here's the weird thing about gases and liquids.
First place. Just can't stay as long on the water. Statistically solid problems.
Colder liquids are actually able to hold more dissolved gases than warmer liquids. So one of the major concerns of climate change is the runaway greenhouse effect. Because as the oceans warm up, they'll actually release more carbon dioxide into the atmosphere. The oceans actually hold a whole lot of dissolved carbon dioxide. They're a huge carbon sink. But if they get warmer, they can't hold as much, and they'll release more carbon dioxide, which will warm up the atmosphere and warm up the oceans more, which will release more carbon dioxide. And you get this never-ending chain, which we term the runaway greenhouse effect, which could severely change the temperature of the atmosphere over time.
Yeah, someone from Utah actually. And Australia.
So it's really like water.
The one from Australia is.
All right, that's all I have for today.
You can show us how to make noise.
All right. Probably not.
I see how it is. Just getting kicked to the side of the curve.
Pay attention to half of the stuff I do when I want you to.
That was half, but none.